This is section 11.3, and this is problem number 2. It says a bar 10 centimeters long with insulated sides is initially at 100 degrees starting at t equals 0. The ends are held at 0 degrees. Find the temperature distribution in the bar at time t. So I did do this problem before, and I've recorded it, but for some reason the audio did not come out. So what I'll do this time, rather than redoing it again, I will go line by line and explain it so I will not write it out like I usually do, because I've already did that, and I will explain line by line exactly what I did. So as I explain the line, I'll scroll below it, so wherever line is showing last, that means I'm explaining that step, that line. Okay, so we have to solve the heat equation. This is the heat equation. Del squared U equal 1 over alpha squared du over dt. U is the temperature. U stands for the temperature. Small t stands for time. Okay, so they didn't want to put capital T for temperature, so they don't confuse capital T with small t. So they're using capital T for U. Okay, so this is a differential equation, and this is called the heat flow equation, and we have to solve it. And the way we do this is by separation of variables. The way separation of variables works is we assume that the actual function that we're trying to solve for, which is the temperature in this case U, okay, is actually a product of functions, of different functions of the variables that are involved in the problem. So for example, here, since we have a temperature dependence on time, then we call this t of t. Okay, so this is some function of t that we are trying to find. We don't know what that is, and we know that this is also spatially varying in x, y, and z, right? So we assume that it's also depending on some function f that is a function of x, y, and z, but we don't know what it is. So these are two functions that we don't know, and we assume that u is actually the product of these two different functions. Okay, this method is general in physics. It's called separation of variables. So the objective is to find out what that f and t is, capital F and capital T. And the way we do this is we start by differentiating and plugging back into the differential equation. That's in general how we solve differential equations, right? We make an assumption on what the solution is, and we substitute it back into the differential equation. So now I am taking derivatives of this equation here. So I will do del squared u, right? And that would be t, because t does not depend on the x, y, and z. Only f does. So it would be some so as far as del squared u is concerned, t is a constant. So this will be t times del squared f. Okay? And the same thing for du over dt. F would be a constant, and du over dt would just be f times dt over dt, right? And so now that means I'm solving for the right hand side of the equation here. Okay, so I'm figuring out what this is. So 1 over alpha squared du over dt equals to 1 over alpha squared. Now du over dt, we said it's just f times dt over dt, right? Because as far as capital T is concerned, f is a constant, so it doesn't change. It's just f times dt over dt. Okay, and we already determined that the left hand side, this is just this. So plug back into the original equation. So you get t del squared f equal 1 over alpha squared f dt over dt. And at this point, what I could do, I could divide by tf, right? Which is actually u. Tf is actually u. I divide the left-hand side, the right-hand side by tf. If I do this on the left, t cancels, and I have 1 over f del squared f. On the right-hand side, the f cancels, and I have 1 over alpha squared 1 over t dt over dt. So this is the original differential equation with my assumptions plugged into it, and then I divided by tf. Okay, now notice that if you look, you notice that the left-hand side is actually function of x, y, and z, while the right-hand side is a function of time. Now, the only way that this can work is if both are constants, because how could a function of x, y, z equal a function of time? That only happens if they're both the same. And they're constants, of course. So then I would call each one of them minus k squared. Okay, since I know that now they're constants. So that means del squared f times 1 over f equal minus k squared, and 1 over alpha squared dt over dt equal minus k squared. And now I could solve this equation separately because it's separated and it's only function of capital T and small t. Yeah, multiply alpha squared on the right hand side and the dt on the right hand side, and integrate both sides. Integral of dt over t is ln t. Here it is. Integral of dt is just t. Alpha squared and k squared are constants. Okay, so that means solve for t, exponentiate this, so t becomes e to the minus alpha squared k squared t. Yeah? Okay, so we are done. So we solved for the temperature. So this is the first part. We achieved the first part of this, yeah? Minus alpha squared k. Of course, k is still an unknown. You don't know what k is.
Right.
Okay, so now let's go to the second part. The second part that I called minus k squared is 1 over f del squared f. So 1 over f del squared f equal minus k squared. Move everything to the left. 0 out the right hand side. You get del squared plus k squared f equals 0. Right? Now, del squared is a function of 3 variables, x, y, and z. So then I broke up this equation in x, y, and z, right? So del squared f in x would be d squared f over dx squared, the second derivative of f with respect to x, plus k squared f equals 0. This is a second order linear differential equation, homogeneous. You know, we've done this many times in differential equation. All you do is you assume solutions in the form of exponentials, right? And then the second derivative would be m squared, if you remember, and then plus k squared equals 0, and you solve for m, and then whatever you get for m, you plug it back into the assumed exponential solution. In other words, if you solve this equation here, I mean, I skipped a few steps, assuming you know that the assumption e to the mx, and you differentiate, you plug back into the differential equation, you get, this is your characteristic equation here, right? You solve it, move k squared to the left, you get an I because it's the square root of a negative number, so m is plus minus ki. And as you know, the complex solutions will get you sines and cosines after you use Euler formula and you change it back to sines and cosines. So f would be c1 cosine kx plus c2 sine kx. Okay, because you plug in the k multiplies the x in the assumed solution. Okay, so we got f. So this is f, and again, We don't have k yet. Okay, so this is solving the left part of the differential equation, and this t here is solving the right part of the differential equation. Now, you might ask, what's with y and z, right? Well, if we look at the question carefully, there's no y and z here, because it said, yeah, because it's just a bar, yeah. So the heat is moving in one dimension. Okay, from left to right. Okay, so that means I don't need the y and the z. So simply this is my f, and now I know that my original assumed solution, which is this here, right, is f times t, and I found both. So now I plug them back in that equation. F times t. This is f, and this is t, capital T. Okay, and u is just the product of these two. You could test it. You could take the second derivative and see if you get 0. Right? Now, what remains to be done is to figure out k using boundary conditions. Now, the question said that at t equals 0, the ends are held at 0 degrees. So this is my first boundary condition here. Okay, at t equals 0, the ends are held at 0 degrees. So that means u of 0 has to equal 0, right? So if you differentiate u, if you plug in 0 into t there, you get 0, e to the 0 is 1, and then cosine 0, because that's at x equals 0, right? Cosine 0 is 1, so you get ax plus b. Okay, fair enough. So u0 is 100, right? Why is u0 100? Because it said in the question, no, initially it's at 100. Yeah, and then starting at t equals 0, the ends are held at 0, meaning when you start, both ends were at 0, but initially, right, it's at 100. So the bar is at 100 degrees. Okay, so that tells me that u of 0 equal 100. Right? You plug it back into this, you get b equal 100. Fair enough? And u of 10, the other end, originally at 0 it's 100. So u of 10 equal 100. You also plug it into the same equation, you get 100 equal 100, or 10a, sorry, this is 10a, plus 100, and you solve for a, you get a equals 0. So that means u of 0 equal 100 at t equals 0. Okay, now we know that at t equals 0, u equals 0, x equals 0, right? Plug this back in here. T equals 0, e to the 0 is 1, x equals 0, the sine term goes away, however, the cosine term is 1, so you get u equals c1, right? But u is 0, that means c1 has to be 0. So this is solving for the first initial condition. And the same thing happens at 10, so now you plug it in, same equation, the final solution. this guy here. Okay, so 0 equals 1 times C2 sine 10k. Same thing, except you're plugging 10 for x instead of 0. And you could solve for k now. So the second boundary condition in this case gets you k, because 1 is the sine, this goes away here, and 1 is the sine 0. It's at n pi, yeah? All multiples of pi, all integer multiples of pi. So that means k equal n pi over 10. Okay, so then having said that, now that we have k, go back into the u equation, which is this. So the whole objective of using boundary conditions is to actually determine what k is. That's the whole point. Here I was just trying to verify that my equation works, yeah? That the flow of heat is actually a linear dependence on x. So that's why I used this stuff here in brown to show you that it actually works, but then I went back here and used my initial conditions in blue. Okay, so now that we know k, just go back here and plug k for what it is. Here, here, and here. Everywhere there is k, I'm gonna plug in n pi over 10. Okay. I mean, I didn't do it here. I could have, but I just left it k squared so I don't crowd this here a lot. But we know what k is now. It's n pi over 10, right? And n could be anything, yeah? N is any integer, 1, 2, 3, 4 to infinity. So that means u is just a summation of the exponential times the sine term and sum it from n equal 1 to infinity, right? Because if we have, it's a superposition, yeah? If I have a solution and another, if I have a solution for n equal 1 and a solution for n equal 2 and a solution for n equal 3, as long as the heat flow equation forms a complete set of solutions, which it does, the general solution would be the sum of these individual solutions. So that's where I bring this summation in, to say that I'm summing all the different solutions for the different n's, multiplying some coefficient an that I don't know, which I need to determine, because I don't know what that coefficient is once I sum them up. It could be different for every term, so that's unknown. Okay, and for that I go back and I plug in one of the conditions, knowing that initially the bar was at 100 temperature, so it's 100 at t equals 0, and I use this to figure out what my an is. So I plug in this here, so 100 equals summation an. Now if you plug in 0 here, this guy becomes 1, yeah? E to the 0 is 1, and you get an sine n pi x 10. Now here I use, so the objective is to find out what this is, okay? And for that, I'm gonna use Fourier Trick. And what that entails is, if you multiply both sides of this equation here by a sine term, sine m pi over 10x, okay? And you integrate both sides, I know that the integral of sine, and that's from a section we covered before, will get you 10 over 2. Okay? We'll get, it's the length, it's basically the length of this interval, 10 minus 0, the integration interval, where the area is, divided by 2. Okay, so that's where that 10 came from. It's 10 minus 0 over 2 times an. Okay. And then on the left hand side, I have sine n pi 10 over x. And, oh, by the way, before I forget, but it's a summation. What happened to all the other terms? Well, it's an orthogonal set, which means when you multiply this summation by another sign, like I multiply it by sine, let me write here with blue, yeah. When I multiply it with sine m pi over 10x, and I take the summation from n equal 1 to infinity, what's going to happen, since this is an orthogonal set, every term will be 0 except when m equal n. And that's when you're going to get sine squared, and that's when the answer will be the length of the interval over 2, which is 10 over 2. So only one of those summation terms will survive. Only one term will survive. Every other term, when you multiply it by sine m pi x over 10, where m does not equal n, and you integrate, the answer will be 0. This is what I'm trying to say. And the only one that will survive this is when they're equal. When m equal n. And you will get 10 over 2. Okay, this is called Fourier trick. You exploit the orthogonality and the completeness of a Fourier series in order to determine the associated coefficients. Okay, and on the left hand side, if I multiply it by sine m pi x over 10, of course I have to do the same on the left. Yeah, so technically you can make this an m if you want. Doesn't matter. And now I just solve for an, obviously. You can integrate this. There's a dx here. That's straightforward. Sine becomes negative cosine, and you divide by the chain rule, which is 10 m pi over m pi over 10, or you could multiply by 10 over m pi. If you want, you could make this an m, from 0 to 10, and then evaluate. And when you evaluate at 10, the 10 cancels the 10, we get cosine n pi. I left the constant out. Yeah, I left this out here. 200 over m pi. You can relabel m to be n, doesn't matter, it's just a dummy variable. Minus, if I plug in 0, cosine 0 is 1. Now cosine n pi can take two values, right? If n is even, 2 pi, 4 pi, 6 pi, 8 pi, etc. Cosine in even multiple of pi is minus 1, is plus 1. Plus 1 minus 1 will get you 0. If n is odd, 1 pi, 3 pi, 5 pi, 7 pi, etc. Cosine n pi will be minus 1. Minus 1 will get you minus 2 times minus 200 over n pi will get you 400 over n pi. If n is odd. Okay, so that means if an is 0, the whole solution is 0, right? The whole thing goes away. So that means I only have heat distribution for odd multiples of pi, because that's when I have an answer for an, 400 over n pi. So now I take that an and I plug it back into this, knowing that I have a summation over the odd ends. The evens doesn't matter at this point, because if the even ones are giving you a 0 solution, you're just adding a 0, so it doesn't matter. So now I plugged it back in, minus 200. There was a 2 from before, minus 2. 400, we already accounted for it here. So 400 over pi, n has to go inside the summation because this summation is dependent on n. And then I plugged in the k for what it is, which is n pi over 10. And then, so the solution for the heat flow distribution will be 400 over pi summation 1 over n. E, the first part, was the solution for the temperature component. and the sine term is the spatial component, temporal then spatial, yeah, spatial component for f. So this would be the final solution that would give you the heat distribution, the temperature distribution in the bar at time t, meaning once I know this, if you were to give me any time, I could tell you exactly what the temperature will be at any point along the bar between 0 and 10 meters. That's what U is. This does it and gives us the temperature distribution in the bar.